Okay. Uh, Today we're going to start a new topic. We'll give you an idea about the non-compartmental pharmacokinetics. It's a very simple topic. Uh, we have exposed to some of these parameters along with other topics, but now we are going to uh, give you the principle of the non-compartmental pharmacokinetics. We'll be covering these learning outcomes, which is the application of non-compartmental approach and also advantages of this model compared to compartmental, and uh, also we will identify new pharmacokinetic parameters like mean residence time, of course, also mean absorption time, mean dissolution time. These can be only determined from the non-compartmental. The area under the moment curve, which will be used in calculation of these parameters. Also, parameters like clearance, also the volume of distribution at steady state. These are also uh, methods to estimate the new useful pharmacokinetic parameters. Also, we will give the limitations of this system and the drawbacks that this system cannot cover or cannot be helpful in defining these issues. First, we need to review. We know all along the course we talked about the compartmental, and most of the topics we consider the one compartment model for those drugs describes this. In the compartmental, the principle depends on trying to fit the data on mathematical equation, differential equations, exponential equation. We knew that drug distribution may varies from one parts of the body than the others. For example, the central compartment, the blood, the equilibration is fast. Together with this, the liver, the kidney. So we consider this the central compartment, and the other parts of the body that drug equilibration takes longer due to blood supply is not high to these organs like fatty tissues, muscles, other tissues. So if the drug disposition is dependent only on the central or fits well with the data with one exponential, this means it's one compartment. But if we see that the equilibration in the other parts also affects the disposition of the drug from the data, we will fit into two exponents. So based on the observation, we try to fit the data into, if it fits in the one exponential, so we consider it one compartment. If there is deviation from the one compartment, we study the data by fitting them into multiple regression equations. And this sometimes will not answer all the questions, and we also found that some drugs needs more than 2-3 compartmental, depending on their the observation of the results. This is the situation in the compartment, and you are familiar with this, and you know how to use the compartmental model. While in this, the non-compartmental, we just apply different principle. Instead of fitting the uh, observed data into multiple regression equations, we can rely on the principle of a statistical theory, a statistical model, which is the uh, statistical moment theory. The moment theory is the main principle. The non-compartmentals depend on it. The idea is a non-compartmental approach analyzes the data without the need to differentiate between the different modes of distribution of the drug. So he analyzes the presence, the confirmed issues, which is uh, the amount of the drug that are present in the system at certain time. And this is also the key for even the compartmental. But uh, in this issue, applying the idea of a statistical moment. The statistical moment is expressing the uh, the individual particles, the individual molecules. So if you give, for example, the dose by a bolus IV in the blood, all the molecules will not will be randomly moving in the body. Some of them will be eliminated, some will distribute in tissue and return it back. So the issue is dependent on something called random motion of these particles. So they are not, they just go by this issue. You have a group of people, for example. The statistical moment is a theory that is applied in many other uh, situations. Yeah. They use it for studying the pattern of movement of people, uh, for example, in crowded places, so they can estimate how much when the time of high accumulations so that they can arrange for this. For example, if people attending a soccer game uh, in the stadium, so they also uh, based on a real data, they can determine how long it takes for the stadium to be filled. And if this is a pattern, they can apply this data on future expectations. For example, before half an hour, they count how many people entered from before 5 minutes, before 10 minutes. So also the evacuation pattern. So they apply the observed data, which is the how many uh, of this individual, and they consider it as uh, a fraction of the total number, with will be entering or exiting at certain time. So they can reach at the end a data called the mean residence time for all people is how long they stay, the mean time for staying, for example. And they can apply this. So the uh, in pharmacokinetics, they found that this is also can be applied to drug molecules. And we can reach uh, a new parameters that is dependent on the observation for how much of the mean residence time of a drug after post administration inside the body, depending on the data that we can get from accessible pools like blood. Sometimes we can get it from the urine too. So we can determine after time interval, certain time interval, how much is present in the body or present in the blood. So from these data, we can get the overall mean residence time applying certain formula, certain simple mathematical formula. So the statistical moment consider the time spent is a random variable, and of course it is a reflection of the mode of drug distribution, but not necessarily to know the mode. You can just tell what is the mean residence time for a drug inside the body. It's something or better explanation than the elimination half-life of a drug. This is directly talks about the residence time inside the body. So again, if we apply this to uh, the pharmacokinetics of drugs, we will assume that the number of molecules n is the total number administered, which is the uh, which is the excuse me. Yeah, I have a lecture right now. After a lecture, okay. Thank you very much. So, sorry for this interruption. So the N is the total number of molecules in a dose, the administered dose, and this will be the total number at time zero before administration, or the zero time, the time of administration, exactly. So we can evaluate how much at certain times, how many is present in the blood by taking sample from the blood. So if we consider after 5 minutes, this T1, T2 after 15 minutes, 30 minutes, 1 hour, 2 hours, 3 hours, 10 hours, and so on, we can get these data. And each parameter of this is considered the time multiplied by the number present in this group. And if we divide this by the total number of molecules, we can remove the numbers from this and we get an average time at the end. We reach an average time by dividing by the n, the number of time. So the general formula for a statistical moment for any mean residence time is the total summation of the residence time for each group of molecules divided by the total number of drug molecules, as we said. So summation of Ni multiplied by Ti. Ni means the number of molecules at present at the time Ti. Yani for example, after 5 minutes, the number of molecules present after 5 minutes, and Ti is the 5 minutes. Okay, so the submission of this the summation of this will give us a value of a multiply of the number of molecules and the time of each group of these molecules, the time they were observed uh, in the blood stream. So We have N is known because this is the dose, the number of molecules present in the dose. So we can determine this simply applying this issue. If N1, we need to determine N1 first, or Ni. For N1 I'll tell N any N. For N1 we can get it from the observations like we see in the plasma concentration time data. From the plasma concentration time data, we obtain uh, uh, a graph of this shape. This is for bolus IV, after bolus IV administration. So each concentration point is a tiny part of the total area under the curve. If we consider at C1, which is representing a time of T1, and we consider this a small minute period, short period. Usually in trapezoidal method, you determine the area of this portion by taking the average between this concentration and this concentration, multiplying, adding them and dividing them by 2. يعني بتاخد الأفريج of the 2 points. Considering that these 2 points are very close, so the average is the same, is the concentration itself. يعني if I'm talking about مثلا 5 microgram per ml or 5.05 microgram per ml. So the average is almost 5. Yani we consider this as the observed concentration as the concentration, but actually it is the average of 2 small concentration in minute minutes. Same thing for the time. We consider this a small interval that in trapezoidal you take T2 minus T1. يعني التايم ده ناقص ده هو length of this one, and to determine the area of this trapezoid you multiply the average of the C concentrations by the difference in time, which presents this part of the curve. If you determine this and divide it by the total area under the curve, this is the fraction of the molecules that is present at this minute period. So that's what is expressed here. If we consider this area under the curve of this trapezoid divided by the total, this will give you a fraction. This fraction, if you take it from the dose, the total dose is represented by the AUC total. You reach that N1 is this fraction AUC of this small trapezoid at C1 divided by the total AUC from 0 to infinity multiplied by the number. For each N1 is determined by this formula. And we know that AUC is concentration multiplied by delta T, the average concentration multiplied by the difference in time in this trapezoid. And this is the total, the magnitude of all trapezoids determined with the estimation of the last, after the last concentration, as you have been using it in the determination of the area under the curve when you determine the bioavailability in the topic discussion before. Okay, so we can say that this Ni equals this amount, the total, this total equation, Ni equals this to this fraction, okay, which can be written like this too. So remember, the formula is talking about Ni multiplied by the time. multiplied by the time. لأنه أنا عايز أجيب التايم الافريج time. Okay, so this amount again will be multiplied by time to determine the t, the time of presence of certain number of molecules. So T1 by N1, then T2 plus T2 by N2 plus T3 by N3 plus T4 by N4 will apply this formula with changing the amount of the concentration present in this each time point. So you can write it as general formula like this: the time multiplied by the n, which is the n is the area under the curve that can be written like this: concentration في delta T على total AUC multiplied by n. If I put n, it will be in the numerator. And this will continue 2, 3, 4 till you reach any number of times, generally Cn at till the end. So this is the total of this, the total of summation is again divided by the number, the total number of molecules. So if you take the n as a common from the all numerators and take it outside this brackets, it will be like this: n taken out of the numerators, so it will be taken as a common outside here, and you have n in the denominator. So this can be taken out with this. So you end up that MRT equals this submission divided by AUC total. AUC is common numerator, so you ممكن نوحد المقامات لأنه كلهم ليهم the same numerator. يبقى بس denominators will be added, which is time multiplied by concentration multiplied by the time again. Okay, and this brings this general formula: summation of Ti multiplied by Ci multiplied by delta T, which is almost the time point, will give, if you add all this till infinity, you end up with something called area under the moment curve. Area under the first moment curve. The first moment curve divided by the AUC. This can give us what is called MRT. Anything is not clear that needs to be clarified more? I just want you to know the principle. The derivatization of the MRT is not required. We will not ask you explain how the MRT equal AUMC by AUC, but it's very important for you to understand why is this formula and where it came from. It came to determine the mean residence time of this drug inside the body, which is the average of the mean of each group of molecules comprising this dose. We said that the dose will not behave the same. The molecules of the same dose will randomly moving inside the body. So some eliminates rapidly, some eliminates after certain periods, and this is a reflection of the interaction of the molecules with the body compartment. So regardless of the mode of distributions, we can tell from the observed concentrations of this drug at different time interval, we can calculate directly without fitting the data into multiple regression equations that takes the average of these points and fit them to straight lines to get the uh, logarithmic equations expressing their movement. So we can rely directly in by a simple dividing of the area under the moment curve by the area under the curve of the drug. This will give us a time. If you see here, this is the formula for AUMC. This is T, time. This AUC is exactly like, this is the formula of AUC. If you see the difference between this will be the time. If we take the average time, this one, this means dividing this by this will give us a time, only time, because we took out the multiplication of C concentration by its time removed, and the only is the magnitude of time of residence, time of all the component, the particles, the molecules comprising the dose. Adding this will give us the mean residence time of the dose inside the body. Any question? The mean residence time is very useful to estimate the duration of a dose, the duration of action of a dose, because as you know, we used to adjust the dose regimen uh, based on the elimination half-life. If the elimination is long, this means the drug resides in the body for longer periods. So avoiding accumulation, we make the interval longer. So on. And this is the main aim of pharmacokinetic, is to use this data to optimize the therapeutic regimens of drugs. So the mean residence time can be more easy, precise, uh, uh, average time that is not like the half-life, which is talking about 50% of the amount eliminated after this time. And this can uh, vary, our variation, and this is high based on the pharmacogenetics difference between people. Still, the MRT will also varies, but since the MRT involves all the points and count them, so the variation will be less than the variation in the uh, elimination half-life. So this is generally the statistical moment formula, which is the n order of time. It depends على time. Moment is the order Tn multiplied by Ct. Ct. So if n is 0, this will give the value of t is always 1, and this will be C multiplied by t, the integration of the multiplication of C multiplied by t multiplied by the time, أو integrated to limited integration to the time. So this will end up with the AUC. The AUC is the integration of the concentration at time t by dt. So when we finish, the integration of this will be C multiplied by t, the summation of C multiplied by t uh, minus at 0 will be 0, and at t equal uh, t or infinity will be the formula of AUC. So this is called the zero order or the zero moment of the statistical moment theory, applying the same formula. In case of n equal 1, you end up with t multiplied by c multiplied again by t, which will lead to the area under the moment curve. So the area under the first moment curve or the first order moment curve is the AUMC, and AUC is the area at the zero order moment curve. This can be applied, as I told you, to any random motion, any random data. And uh, as you see it again, this is the summary of this. So when you take this out, so you have average time, mean residence time, which is this. By dividing this by this, you get this average time, the total time of the particles stayed inside the body, the mean time for them. And in practice, how can we determine AUMC? We know how to determine AUC, but how can we get this plot? The area under the moment curve, as I told you, is C multiplied by T. Again, this uh, is plotted against the time. So we, in order to get this, we will introduce a new plot. This plot is obtained in its y-axis by the multiply of the concentration, plasma concentration, multiplied by the time point. This, or the, the, the sampling time point of this concentration. We multiply each concentration, plasma concentration, by its sampling time. And we plot this against the time. So we will have a new graph like this. So forget this part as if this is not present. This is the observed plasma concentration after time. This the left graph in the left y axis. ده بلوت العادي اللي هو بين plasma drug concentration and the time. This is observed. For example, this is after 2 hours, 4 hours, and so on, 6 hours, 8 hours, 10 hours, 12 hours, the sample, and we see the decline of the concentration post-administration till it almost approaches zero. Now after 24 hours, a small, minute amount is still present. So on. This is the normal observed data. So we can determine the AUC of this curve simply by dividing this into trapezoids, and we can determine the area of these trapezoids. We add them together till the end, so we reach the area under the plasma concentration time curve, which is the area under the zero order moment curve. Okay. طيب. In order to get the AUMC, we need to plot a new data. The data is based on the observation. For example, we have this one. Assume this is 6 microgram per or milligram per liter, observed after 2 hours, for example. So I have 2 hours, 6 milligram per liter. After 4 hours, I have 4 milligram per liter. After 6 hours, I have almost 2 or 2.1 milligram per liter. if we put this here, for example, like this, concentration CP, and this is the time T, and we put, as I told you, 2 or 2 hours, 4 after 4 hours, no, sorry, 6, this is 6, and 2 or 6 hours, and so on, all the data. So in order to have to plot the AUMC, you get the C multiplied by T. CT is obtained like this, multiplication of both. CT here for this point is 12. C is 6 by 2, 12. 6 by 4 by 4 is 16. 6 by 2 is again 12. And so on. So you built a new y-axis called C by T, which is the first moment curve. In order to draw, you again plot this against the time points, against the time point, the time in the middle. So this time with the CB gives you the area under the curve. The same time points against the multiply of concentration CB by T, CB, this is B, CB by T equal. So look at this curve, how they developed. They developed this one. This is the AUMC using this y-axis. Forget the left one. And now we put the two y's to just compare how they correlate to each other. They correlate that the same x is used, the same time points, sampling points is used. But for this one, for example, if we plot with the values of this after 2 hours, 2 hours, it's like this one, the same point, to the observed concentration is here. Here is 12. Don't forget this y-axis. This is not present here. This point كأن الواي ده هو اللي هنا. هتلاقي this is equivalent to 12. طيب at 4 ادي 4 time point قلنا تكون 16. This point is 16 here and this y-axis. Okay. Again, the 6 after 6 hours. طيب 6 hours المفروض يكون ايه 12. 6 hours اهو 6 hours هنا كام 6 by 2 gives rise to this point اهي 12 this one okay, this is equivalent to this is equivalent to this is a 12 again. طبعا في variation, he has not 2 exactly and it's 2 by something, so this makes the variation. لكن the same principle. This one is a time point مثلا 10 or 8 or whatever multiplied by the observed. If the concentration here is less, لكن still the multiply this concentration by the time plotted here, it will be develop a curve like this. So the AUMC curve is a bell-shaped curve that is obtained by plotting the multiply of the plasma concentration by the sampling time of this concentration in the y-axis against the sampling time again. Obtaining a new graph, this graph will be, the area under this graph will be determined by the same trapezoidal method. The same trapezoidal method will be used to determine the area under the UMC curve, AUMC. If we take this area, divide the AUMC by the AUC, we end up with the mean residence time, exactly like this. So we can determine them using the trapezoidal method. طبعا we know في الtrapezoidal method till the last sampling time, and we will not reach zero. For example, we can estimate the terminal part of the terminal area, or the area of the terminal part after the last concentration point. And this will be determined by the same trapezoidal method اللي divides the area to trapezoids. The trapezoids will have the average of these two uh, uh, dimensions اللي هم العرض في متوسط الأطوال للترابيزويد. فالمتوسط ده will be determined by a الطول ده بيعبر عن C1 وده C2. C1 plus C2 على 2، يبقى المتوسط بتاعه ما يبقى something in the middle. والتايم is T2 minus T1، لأن دي مثلا 6 ودي 4، يبقى 6 minus 4 يعني 2. يبقى length of this part is 2 hours أو 2 minutes أو whatever. فعشان نعين ده بالترابيزويد we determine it like this. T2, this is a formula of the trapezoidal method. T2 minus T1 multiplied by the average concentration عشان يديني الاريا. الاريا مساحة الشبه المنحرف هي متوسط الضلعين دول في الضلع ده. الضلع دايما ثابت ما بيتغيرش، لكن دول اللي مختلفين. الافريج of this C1 C2 الأطوال دي بعبر عنها C1 لأن الطول ده جه من الكونسنتريشن ده. ف this is a general form. في حالة ال AUMC لا، الواي اكسس عندي مش C، T multiplied by C. Yes, الاكس اكسس the same، فهنلاقي الترابيزويد ليه نفس الاكس اكسس، لكن الواي هو متوسط النقطتين دول في ال AUMC بلوت ايه مش concentration multiplied by time against time، فيبقى CT minus C1 في T1 و C2 في T2. فالافريج هنا يبقى الافريج of T2 في C2 plus T1 في C1 على 2 بس. This is the formula. You are going to determine the mean residence time in the I think this week in the topic discussion session. You will also determine other non-compartmental parameters too in these lectures. So the estimation of the terminal part, as you used to do it in the determination of AUC from T last to infinity، لأنه هنا you can determine the trapezoid till the last sampling point. لكن in this part, if we consider this is the last, after this we need to estimate the remaining till infinity. So we used to determine the last concentration we divided by what is called pi. What is pi? Pi is the slope of the terminal phase of the plasma drug concentration time profile in a semi-log scale. يعني K احنا اللي هي الانالوج of K. Pi or K اللي هي elimination rate constant is the slope of the line when we plotted in a semi-log paper. So this will be, in the case of AUMC, will be the uh, you divide the last point اللي هي عبارة عن last time point sampling time multiplied by the last plasma concentration divided by K, and you add to it the last sampling point divided by K square or pi square. Pi or K are analog of the same thing. Yes, we obtain this by plotting the data into a semi-log paper. The slope of the line will be the K. Okay, so this is the first none of the basic non-compartmental parameter, pharmacokinetic parameter, which is not present in the compartmental model. The mean residence times expresses the mean time of the dose, or the mean time of the molecules of the dose that they spend inside the body. And of course, it's indirect interpretation of all the processes, including the distribution modes in various tissues and the elimination mode of the drug, the protein binding of the drug, the also metabolism rate of the drug. All these can be reflected in the mean residence time without the need of assuming the compartmental or multiple compartmental models. Okay, any question? Yeah. I hope so. Okay. طيب, we will continue the rest of the lecture in the on Tuesday. Thank you.